Okay, we are on section 14.2. Limits and continuity of multiple variable functions. Just like with single variable functions, we are going to talk about all the same things. So we've got to talk about limits and continuity, just like we did in single variable. So we're going to be able to determine the limit of a multivariable function and discuss the continuity. All right, so the goal of this table is for f of xy, which equals sine of x squared plus y squared over x squared plus y squared. What does f of xy approach as xy approaches the point 0, 0? So from Calc 1, there are a bunch of things that we should try. The first of those is you should probably try direct substitution. Direct substitution. And if you directly substitute in 0 and 0 in for x and y, you're going to get sine of 0, which is 0, over top of 0. That is a problem. That is bad. We don't like that one. What else can we try? We can try L'Hopital's rule because we got the 0 on the top and the bottom. The problem is we're doing L'Hopital's rule with multiple variables, so that is going to be an issue. Can't do it. We could definitely try factoring. In this case, there is nothing to factor. If that was x squared minus y squared on the bottom, maybe we'd have something to go with, but we don't. What else can we think of? Let's see. We can always try multiplying by a conjugate. That's another method from limits. And in this case, there's no conjugate. I mean, you could multiply the top and the bottom by x squared minus y squared, but it won't do us any good. So that one's bad. If all of that fails, because we have it, we can look at our table. You won't always have a table, but we could probably create a numeric table of values. So we could definitely say a table of values is probably more accurate to figure this thing out. So if we look at our table, because the table was given, I mean, really, this is pretty obvious, at least I think it is. If we look at the table, as x approaches 0, or excuse me, as the x values are 0, no, we'll say it again. As x approaches 0, we are looking at these values right here. As x approaches 0, we're looking at those values right there. Specifically, hard to go back and forth here, it's as x approaches 0 from either side. Those are the x values. What is the function approaching? But it's not enough just that x looks like it's approaching 1. We also have to check the y direction. So in the y direction, we're looking at these values as y approaches 0. So we are looking in this direction as y approaches 0. And of course, it looks like all of these values are converging to 1. So we would say that the limit of f of xy as xy approaches the point 0, 0 is 1. Okay, and that's the way you would do it using a table. Not necessarily going to always be the easiest way to do it. All right, but that's the general idea using a table. So let's kind of go back in time, back to when we did two-dimensional limits. Let's go through the concept of a two-dimensional limit. So if you've got some kind of a function, whatever this thing looks like, and maybe there's a hole right there, and then the function goes off that way, whatever the function does. If this hole right there is represented by x equals a, it's going to give you some kind of a value up here, f of a, or we'll call it b in this case. There is no f of a because that point does not exist. What we would say is the limit as x approaches a of f of x is b. And remember that the idea was, as a matter of fact, let's go ahead and we'll throw a point up here. Okay, that's actually f of a right there on top. The idea was, what does the y value approach as x is approaching a? It's not the actual y value, because that is obviously above it now that I've defined it there. It's what does the y value approach? It's what the limit is, not the actual value of the function. So ultimately, in order to get that, what we would have to say is that the limit as x approaches a from the left side of f of x equals the limit as x approaches a from the right side of f of x. And in this case, they both approach b. They would have to approach the same thing. And in our case, I don't know, let's define this point up here as c. F of a would equal c. Okay, so obviously this one would not be continuous because the limit doesn't equal the function's value. But that's how we did a limit in 2 dimensions. Not that easy to do in 3 dimensions. So the 3-dimensional idea, presented first in 2 dimensions, because believe me, presenting the 3-dimensional idea in 2 dimensions is hard enough as it is. All right, so let's say, as a matter of fact, I'm going to erase that. You'll see why I'm drawing it this way in a second. All right, so let's say that our function looks like this. Got a hole there. Actually, no, let's not even say that. I apologize. Let's just say that we have a hole right where I drew that hole. So I guess the best way to start this would be like, okay, so we're trying to figure out as xy approaches 0, 0, what the limit of some function would be. So I guess we're going to go back to what I said in the first place. So sorry for that if you keep erasing and stuff. Let's start off with something that looks like this. So that would be like y equals x squared. So the idea is, what is the limit as x approaches 0, 0? Well, if we do the y equals x squared thing, the limit as x approaches 0, 0, I'm trying to think of the best way to state this. If it's just the parabola, we have a limit. Okay, it's going to approach 0. There's no problem there. But the problem is, in order for a limit to exist, the limit of our function of xy, whatever that happens to be in 3 dimensions, as xy approaches the point 0, 0, will only exist if every curve C will approach the same limit L. Will approach the same limit L. So what do I mean by that? I mean that every possible curve that we could draw along our surface, and again, you have to think of this in kind of 3 dimensions as well, every possible path that we could take that's a function that would approach 0, 0 in this case would all have to give exactly the same limit. So what do I mean by that? Well, we could approach this curve as it's set up right now. We could approach it from y equals x squared, and you would have a whole bunch of values which are approaching 0. So that would not be a problem. But you also have to approach it from everything else. So this line, y equals x, would also have to approach 0, 0. You would also have to approach 0, 0 from the x-axis. It's kind of hard to draw, and I apologize. I'm doing my best there. You would also have to approach 0, 0 from the y-axis. So basically, the idea is every single possible path that leads to the point 0, 0 would have to give exactly the same limit. So the way to kind of equate this to the two dimensions is that there's only two paths in two dimensions you can get. You can approach from the right, you can approach from the left. That's it. On a three-dimensional surface, you can approach from almost an infinite number of paths. There's an infinite number of ways to approach a certain point. It's not just two directions. You can approach from the x in the x direction. You can approach in the y direction. We can approach in all kinds of different methods. Again, you have to picture a three-dimensional surface, and some point on that surface, you can approach from an infinite number of directions. That's going to be very difficult to do, okay? But it is going to at least give us the idea of what we're going to try to be able to show a limit of some kind. All right, let's do an example. I think it'll make more sense. All right, so what we have is we have the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared. By the way, the reason we're using 0, 0 in this case is because a lot of times what you're going to end up with is some kind of form of 0 over 0 in this case. If this was as xy approaches 1, 2, we have no problems whatsoever. We just plug 1 and 2 in and you're done. So again, direct substitution always should be your first thing to try. So here is our general order. We are going to try to evaluate the limit, first of all, along the path, after you try direct substitution, along the path of the x-axis. Then you'll try it along the y-axis. Then you might try the line y equals x. And then if those things don't give you anything specific, then you're going to have to do a little bit of thinking. There are a lot of other paths that we could choose, but we need to kind of try to be strategic as to what it is so that we can figure this out. In all honesty, most of the time, these are going to come out to be failing to exist, but I'll show you how that works too. All right, so let's try a path along the x-axis. So if we try a path along the x-axis, if we take values which are all on the x-axis, the y values are 0. So anything on the x-axis, the y values are 0. So you would have the limit as xy approaches 0, 0. If the y values are 0, all you have left is x squared over x squared. And of course, you simplify before you reapply the limit, because if you plug 0 and 0 in right now, you would still get 0 over 0. But we're going to apply the fact that x squared divided by x squared, first of all, is 1. So now you're just taking the limit of a constant. The limit of 1 is 1. Okay, I didn't write all that out, but I hope that you understand that one. Now let's try it along the y-axis. So we would take the limit as xy approaches 0, 0. Now if we're on the y-axis, the x values are 0. So now what I end up with is negative y squared over y squared. Simplifying that one equals negative 1. Well, the limit as you approach from the x-axis does not equal the limit as you approach from the y-axis. Therefore, this limit fails to exist. And yes, I know we're so used to writing DNE for does not exist. For whatever reason, they've changed it to fails to exist in 3 dimensions. I have absolutely no idea why, but it is FTE now. It fails to exist. Okay, so hopefully you can see that we've tried to approach the limit from the x-axis and the y-axis. They were 2 different limits. Because of that, the limit fails to exist. All the limits have to give you the same L. In this case, L was 1 or L was negative 1, depending on the path. Number 2, similar idea. Let's try the x-axis first, because obviously plugging 0, 0 in gives us 0 on top of 0, and that's a problem. So if we approach from the x-axis, we'll have the limit as xy approaches 0, 0. That's probably the most tedious part, is writing that down. If we're on the x-axis, that means the y values are 0. So what I get is 0 over x squared. Simplifying, the first thing you do is you simplify 0 over x squared. That's 0, so the limit is 0. Let's try the y-axis. Okay, along the y-axis, that means as x approaches 0, 0, along the y-axis means x is 0. If I plug 0 in for x, I end up with 0 over y squared. Of course, 0 over y squared is 0, so that limit is also 0. Okay, so we've approached from the x-axis and the y-axis so far, and they've both given us 0. But remember, every single possible path has to be the same. Let's try y along the line y equals x. Okay, if we try along the line y equals x, our limit of xy as x, our limit of the function as xy approaches 0, 0 is going to be, now if y equals x, that means I can substitute y in for every x, or x in for every y. It doesn't really matter. I'm going to plug y in for x. So that means on the top I'm going to get y squared, and on the bottom I'm going to get y squared plus y squared. Y squared over 2y squared simplifies to 1/2. So that limit is a half. Because all three of those are not the same, we found one that was different. This limit fails to exist. And we had to show 3 different paths in that case if we went in our standard order. Okay, let's do another one. So once again, if you plug in 0 and 0, you get 0 on top of 0. So let's try the x-axis. So we will take the limit of xy approaching 0, 0 of our function. So on the x-axis, the y values are 0, so we get 0 on top of x squared. Of course, that is 0. We try the y-axis. Limit as xy approaches 0, 0. That's going to give me 0 over y to the 4th. That is also 0. Okay, let's try the line y equals x. Limit xy approaches 0, 0. So if I substitute in y for all the x's, so I'm going to get y cubed on top over, what's that going to be, y squared plus y to the 4th on the bottom. Remember to simplify first. This is not good notation, what I'm getting ready to do, by the way. I can factor and divide everything by y squared, so I'm going to get a y over 1 plus y squared. If you were to plug in 0 and 0, you are going to still end up with 0 over 1, which is 0. So far, every path has given us the same thing. So let's try something different. Let's try, instead of x equals y squared, let's try that y equals x squared. No, I'm sorry. Let's turn that around because that one actually won't work. So this is where you have to do a little bit of thinking. X equals y squared. So if x equals y squared, so for every x, I'm going to plug in y squared. So the limit xy approaches 0, 0. So we're going to get y squared times y squared on top over y squared squared plus y to the 4th. So maybe you can see why I picked that specific one, because now I'm going to get a y to the 4th over y to the 4th plus y to the 4th. So really what I have is 1y to the 4th over 2y to the 4th. The y to the 4ths all divide out, and you're left with 1/2. So after all of that, this one fails to exist as well, because 1/2 is different than zeros. Okay, you're probably starting to see a pattern here that most of these do not exist or fail to exist, and that is true. We're going to come back and do number 4. Number 4 is a bit more challenging, but we'll probably only need one more video to finish this off.